The next group of factors that define the way solid elements behave as part of the passive solar systems and the extent to which they use the solar radiation to turn it into warmth. Consider the elements themselves. And of course, the first thing is their orientation. It has to be good enough to allow enough solar radiation to reach them. And also their surface uh, uh, must allow fast and enough amount of solar radiation to be absorbed and to transfer that solar radiation and uh, to the main material of the solid elements. And the main material needs to have a good speed of absorbing and accumulating the solar radiation and high heat capacity to it has to have the ability to absorb enough amount of heat to generate enough amount of heat and to keep it inside for long enough time so it can be radiated back to the spaces we need at the proper period, let's say during the night or during colder seasons. So the surface of the solid elements, usually the solid elements of the buildings are layered elements. They have several layers. So they have two surfaces, outer and inner, or on the other side, on the one side and on the other side. And so the surface to which the solar radiation first reaches has to to have proper color and proper texture for whatever use we need it for. And here are some examples that show the material of the surfaces and the color of the surfaces from white to black and lighter shades and darker shades, and the percent of the solar radiation reflected back. So when we have asphalt, um, we have 3 to 18% reflected back. That means the other amount of the solar radiation is absorbed and transferred to the main material of the element. Then we have some metal coverings, um, uh, roof coverings, traditional ceramic roof coverings, and reflecting metal folio, which is used on some roofs, for example, on gas station roofs to prevent overheating because of the fire safety. And again, white color reflects back up to 90% of the solar radiation, while black color reflects less than 20%. It means that 80 and above percent of the solar radiation is accumulated and then transferred into heat. And the other factor, the other property the element surface should have is its texture. Uh, the more rough it is, the better, because sometimes, although it cannot be seen with um, bare eyes, um, the surface of the element enlarges up to 30% because of the rough surface texture. because of the rough texture. The next factor is the main material of the elements. And here, the building elements are can be divided in two types. The first are so-called white buildings with white elements, and then the others are heavy buildings with heavy building elements. The first group are materials based on contemporary petrol-based industry. They usually consist of a layer of effective isolation covered for protection with uh, thin layers of other materials. They can be cardboards or metal or wood, and the layer of the effective isolation can be again petrol-based penopolystyrol or stone mineral wool or some other effective insulation. So the positive qualities of these kind of building elements are they have small density. Because of the active insulation, they need to be thinner walls and roof coverings. They are white. They're about 25 to 30 kilograms per square meter. They have good isolation properties, and they are stable during earthquakes because of their small mass. They don't gain this momentum, which is very dangerous during the earthquakes. So they don't start to shatter stronger and stronger because of their mass during the earthquakes. But the negative properties are that they have very low heat capacity. Such building elements with active insulation have uh, uh, don't have the proper materials to store the heat inside and to keep it for a longer period of time. So buildings with such elements require permanently working active climatic system, no matter warming or heating system or cooling system. It has to work permanently all the time because the minute it's turned off, the temperature levels change very rapidly. That is very fast. They go from comfortably warm to uncomfortably cold, or the opposite in summer, from comfortably cool to uncomfortably hot. And because of their lowered mass, they are very vulnerable to wind shatterings. Uh, the wind can be felt in such buildings, even if it's not that strong. The other type of the buildings, the heavy buildings, are built with heavy, with elements, with heavy materials. These are usually the traditional buildings the stone materials, bricks, and concrete. So they have very high density, which means that they are very happy. The positive qualities are that they have very high thermal capacity. They can store a huge amount of warmth inside and keep it for a long time. Of course, they need long period to gather that heat inside, but then they radiate it for long time and constantly. Uh, so these are the elements with these materials that allow building passive heating systems and passive buildings that don't have active heating or cooling systems. Because of their high thermal capacity, they allow the change of the temperature levels to happen gradually and slowly in time. And of course, they're very stable against wind shatterings because they're too heavy. There is no wind that can shatter them. The negative qualities of buildings, of heavy buildings with heavy materials of their solid elements, is that the walls and the roof had to be thicker with greater thickness to ensure the thermal insulation. They are heavy, about 250 up to 300 kilograms per square meter, which means that the construction has to be stronger with bigger elements itself. And they have a lower uh, insulation properties. These materials don't keep that warm or cool as the effective insulations, and they're vulnerable to earthquake because they gather big momentum during the earthquakes. So when the gathered heat have to be distributed uh, to the living spaces, it is distributed through radiation and through convection. To distribute it evenly in all the space, all the rooms where we need it. Usually, we open the doors between the rooms. We seek some natural ventilation to happen better. And if natural ventilation is not enough, sometimes additional semi-active and active systems of tubes for transferring the heated air are built inside the buildings. And this is the formula to calculate the the way a solid building element allows the heat to transfer through it from one area to another. It depends upon the thickness of the element, but measured in meters, because the measure unit includes meters. So if we have 25 centimeters brick wall, in the formula, we put its thickness 0.25 meters. And of course, it depends upon the material and its specific um, coefficient of heat transferring of the material, because brick transfers heat at one extent and the stone at other, and concrete has another this specific coefficient of heat transferring. And of course, the thicker the bigger the thickness is, the final result changes, because 12 centimeters of brick and 25 centimeters of brick and 38 centimeters of brick walls have the same material with the same specific coefficient of heat transferring, but the final coefficient of heat passing resistance um, is differs because of the thickness. So usually the normative requirements give this coefficient. It's of heat passing. But to find the element's coefficient of heat passing and to compare it with the normative requirements, we need first to calculate its reverse coefficient of heat passing resistance. And it is calculated using the thickness of the element and the specific coefficient of the material. Since it was already mentioned that the solid elements in the buildings are layered elements, all the warmth passing resistance coefficient of each single layer is calculated, then they're summed, and the sum after that is reversed to have the coefficient of thermal passing of the summed coefficient of thermal passing of the element, and this u, and it's compared with the normative requirements. The normative requirements set the upper limit of how much heat should pass through the outer surface of the element per square meter. The more is not okay, and the less that the normative requirements set is okay. So the normative requirements say this is the upper limit, and if the wall or the roof lets more of that quality, sorry, more of that amount to pass through and to be radiated to the outer atmosphere, so this element is not okay and needs additional measurements. Usually, this is the way to calculate a building solid element coefficient. A, a schema of the layers of the element, some explanation, and this is the thickness in meters and the specific coefficient of each single material, the final result, and also adding two air layers adjacent to the wall. They are they are centimeter thick, and the one is in it next to the inside surface of the wall, and the other is next to the outer surface of the wall. They are not calculated; they are just added. They're they can be taken ready without calculation, and then all these results are summed and then reversed to get the final coefficient of heat passing of the wall and compared with the normative requirements. As it's seen here, a simple brick 25 centimeters brick wall with two finishing layers is definitely not enough according to contemporary requirements. These are the two tables with the air layers, adjacent air layers. The inner air layers have the same these numbers because, as it was said in lecture 2, what is required is an equal radiational temperature of all the surfaces, and it is supposed that that is why the inner layers of air adjacent to the inner surfaces have the same amount, not, but I can't remember the word. They have the same numbers. However, the outside layers adjacent to the outside surfaces of different building solid elements, it differs, and this is the outer layer of air adjacent to roofs, where the heat goes up from downside up. This is for walls where the heat goes horizontally, tries to escape the room in horizontal direction, and this is for floors where the heat uh, escapes the room in vertical direction, but coming from up to downside. Such cases are when part of the room goes outside, on the second floor goes outside, and a part of its floor uh, contacts the air. And these are the more uncomfortable parts because the floor gets too cold. And this is another table that only shows one and the same surface material and the speed of air movement, the speed of wind, and the way the heat loss changes when the wind is only 1 meter per second, and when it's 10 meter per second, it's almost three and a half more heat lost through the same surface with the same material. When estimated that the building element does not have the proper coefficient as the normative requirements, the most common measure is to add a layer of effective insulation. And this is a comparing illustration of wall without insulation, wall with outer insulation, and wall with inner insulation. When we have minus 15 degrees outside and we keep about 20 degrees inside, the transfer from negative temperature levels to positive happens in the main building material, somewhere in its thickness, which means that all the freezing and then and condensing happens in the main material of the building element, and it is much destructive. Both processes, water freezing and condensing, are destructive processes because the first one, when water freezes, it enlarges its volume and thus mechanically destroys the material around it. And then when it gets warm, it liquefies and washes away, but the caverns that were created stay and gather even bigger amount of water than that again freezes and destroys even more. And the second process of condensing washes away the more water vulnerable minerals of the material. When placing out effective insulation on the outside, this 0 point doesn't happen anymore in the main material. The main material is also protected from aging because of ultraviolet sun rays, and it has the ability to absorb the heat from the outside, but not to radiate it to the outside and to radiate it back to the room when needed. The problems with the outer insulation is that the montage process is difficult. Uh, it needs additional some stairs and ropes. It needs also it has to be thicker, 10 centimeters, 15 centimeters, according to the material. And it also needs an additional protecting layer from the outside, because to protect the insulation itself from mechanical destroying and from ultraviolet aging. And this additional layer needs additional work and additional materials. When in cases when placing insulation from the outside is for some reasons impossible, there is an inner insulation, and it's much easier to be placed. It has to be much thinner, about centimeter or two, because its sole purpose is just to uh, protect the walls to accumulate the warmth from inside the room. However, it's not that good for the wall, because again we have the 0 point happening in the main material. Sometimes the main material is still vulnerable to outside destroying processes, and we don't use the thermal capacity of the solid main material of the building element for passive heating of the rooms inside. And the other specific moment for the inside insulation is that should be placed not only on walls, but the whole room should be covered. All the inner surfaces should be covered with insulation, because otherwise, if only walls are covered but the floor and the ceiling stay uncovered, they are cooler, and so we have a warmer surface of the wall meeting cooler surfaces of the floor and the ceiling, and usually there starts some condensing and some this microplantation processes, mosses and other not okay for inhabitants' health processes happening. Different kinds of effective insulations used so far for improving energy efficiency behavior of buildings. The first group is developed earlier than the others, and is the most common and most used. They are insulations based upon petrol materials, petrol-based products, um, panopolystyrols, and they are three kinds. Expanded polystyrol, which is older as technology, and in which the single granules filled with air are heated, they expand, and then they are pressed together while they are hot, and they glue to each other, stick to each other, and this way these elements are formed. However, this kind of insulation is very unstable. It can be easily mechanically destroyed, and has lower qualities. The second one is extruded panopolystyrol. It has different trademarks as Fibran or Styrodur, but it is one and the same project, extruded product. Extruded panopolystyrol. Its technology is a little bit different. A certain mass of pen polystyrol is filled with small gas bubbles and then baked, and it extrudes enlarges its thickness, and after that it's cut in the form it is needed, and thus it's much more stable and has higher insulation properties. And the third one is polyurethane foam, which is used in places where the previous two are not good enough. The montage will be difficult, and usually where too much small gaps between the elements happen. So the foam why expands itself and fills that gaps, which the other two are unable to fill. Both all three based on petrol-based insulations easily burn, and during burning radiate dangerous for health and for life emissions, and have relatively a short life because they age very fast and they are easily destroyed. The next group are isolations, effective isolations, with in which the air is kept inside with uh, materials extracted from stones and sometimes from glass, stone and glass walls. And they came in soft forms and in hard plates, which are used for floors and terraces and roof terraces. So they are not so easily destroyed by stepping or placing furniture on them. They do not burn and don't radiate dangerous for health and life emissions, but they are more expensive. The third group are effective insulations using agricultural wastes, plant wastes, some straw, and some waste from the wooden industry, uh, and they are much financially appropriate. Sometimes their price um, is about 20 times lower than, let's say, the petrol based insulations. But they, of course, they have some negative properties. First, the elements usually are about 50 centimeters thick. The technology to produce thinner elements is still not developed enough. And also, they need additional ensuring that some insects won't start to develop inside them. But they're also very good sound insulators, except heat insulators. And there are buildings in America built with such kind of elements that are about 80 up to 100 years old and still behaving absolutely properly. And of course, isolations with some wood particles from the wooden industry. This is another kind of effective insulation, and it's called a foam glass. And its technology is very similar to extruded penopolystyrol. So some mass of glass is filled with air bubbles and then baked, and the material gets this view. It's actually very white and can be transported by hand and cut in by hand. But on the other side, it's very sturdy. It's difficult to be mechanically destroyed, and it has 50 years up to 100 years uh, security period that it will work properly. Of course, it requires um, much initial money, but after that it doesn't require any changing after 15 or 20 years, and it keeps its properties for at least 50 years, and the producers say up to 100 years. And the next several isolations are based upon cosmic researches for space researches for space stations. And the first one that is already entering the market is Aerogel, which is uh, which has nickel phosphor tubes with very small, about 100 nanometers thickness, filled with air, and placed in a grid. And it is for real what is shown on the third picture, because I've seen it as a demonstration on science conference here in Bulgaria, but in Varna, and it definitely doesn't allow any heat to pass through it. However, it's really expensive. It's about 300 euros per square meter so far, and it's not very, for that reason, used massively in buildings. But it has one of the form. It is one of its form is in this kind of sheets, but the other is in form of a gel, and it can be impregnated in the layers of the solid elements, and especially when the building is architectural monument and its facade design is important for the town, and it's important to be kept as it is in its original design with its original elements. The gel form of that aerogel is very uh, appropriate, but still too expensive. And the next one is vacuum isolation. Again, a space research product, and it contains inside tubes that are actually with vacuum, but not with air. And vacuum is even better for preventing heat exchange than air. um, and of course, again, too expensive. And additionally, the metal folio reflects back the solar radiation, but it requires some additional wooden construction, and it can cause condensing because of the metal covering. And the last one is again, um, it's a transparent nano insulation, which is which is meant to replace windows, and thus improving the thermal loss to through transparent elements, and replacing glass, which is heavy material, and also because of its processing is still a very expensive material.